over some basics of E&M and vector algebra. So, essentially, electricity and magnetism deals with the motion and change of what we call fields. Now, there's probably already one field that you're familiar with from high school physics, and that's a gravitational field. Now, if you take a large object, like let's say it's the Earth, this has a gravitational field. How? Well, if there's something in the distance, like for example the moon, the Earth attracts that thing in the distance towards itself. So, it has a gravitational field that gets stronger and stronger as you get closer and closer to it. So, it dissipates as you go farther away, but it's always there, even if it's just the tiniest little pull. So that is a gravitational field. And by Newton's laws of gravity, we can figure out the magnitude of this gravitational field at any point in space. So it's just g, the gravitational constant, times the mass of the body that's exerting the field, divided by r squared, which is the distance between the body and whatever point mass we're talking about.
Is it big M or small m?
It's big M, because the big M is the one that's exerting the gravitational field. Small m is the one that's inside the gravitational field. So, this is our gravitational field. Or acceleration due to gravity. When we're near the surface of the Earth, the gravitational field is basically constant because it only changes radially, and the Earth is approximately a sphere. So, close to home, it's basically the same value, 9.8 meters per second squared. So now, we can do a very similar thing with electricity and magnets. Today, we're going to be talking about electrostatics. So there are two types of charges, positive charges and negative charges. Now, when we're talking about gravitational fields, these fields only point inwards towards whatever body we're talking about, only attracts. It's not like there's some body out there that will repel anything that gets close to it gravitationally. However, while an electron or a negative charges field may look somewhat like you expect, a positive charges field will actually point outwards. So, and you might ask, what is this field anyway? Well, if we take, in the case of gravitation, if we take the mass of an object and multiply it by the gravitational field at that point, this is going to give us the force that is exerted on the mass. So, in the same way, if we take the charge of one of these things and multiply it by the electric field at that point, that gives us the force exerted on it at that point. So, that's why electric fields are so important. So now, if you sum up a positive charges field and negative charges field, it'll give you what we call a dipole. So it'll look something like this. And you've probably seen this diagram at least once or twice in your high school physics class. So this is what we call a dipole. And finally, we're going to be learning how the electric field changes. The electric field is just kq over r squared, and this is actually the magnitude of the electric field at some point. So, no, it didn't check. So, looks pretty similar to the other one where we have gm over r squared. We just got that inverse square law going.
In this case, is it also BQ?
Yes, it is. So, this all works out. And so finally, let's do some basic vector algebra. So let's say we've got a positive charge here, 3 meters south, we have a negative charge here, and 3 meters east, we've got a positive charge. Now what I'm going to say is this charge is 1 microcoulomb. This charge is also 1 microcoulomb. This charge is negative 2 microcoulombs. So now, let's say that I decide to place a fourth charge right over here in the middle. So this is a positive charge with charge 3 microcoulombs. What is the net force at this point? Well, all we have to do is first find the electric field, then multiply by the charge. So, what's the net electric field? Should be pretty easy, right? Well, we have that it's being repulsed in this direction. It's also being repulsed in this direction. But without having to do any math, let's think about it. This has the same charge as this. And they're both pointing in this. They both are pointing in opposite directions. So these have the same magnitude but opposite direction, meaning they should cancel out. So we don't even have to do any math, which means the only force that we have to consider is the force coming from this negative charge. So, as you might expect, this is coming at a 180, 45, a 225 degree angle from the horizontal. But to make the algebra simpler, we're just going to start doing math from here, making this only a 45 degree angle. So this is minus 2 microcoulombs, and this is 3 microcoulombs. So what's the actual force? Well, it's K, whose value is 9 times 10 to the 9, times the charge of one of them, 3 microcoulombs, times the charge of the other one, 2 microcoulombs. And we only use absolute values here. We figure out the direction on our own. Divided by r squared. So what's the distance between them? Well, now we have to do a little bit of geometry. 3 by 3. Got the midpoint over here. So what's this? Well, this is 1.5 root 2. So this also has to be 1.5 root 2. Or 3 root 2 over 2, if you choose to write it that way. So we've got 3 root 2 over 2 squared. How do we write that? Well, that's just 3 squared, which is 9, times root 2 over 2 squared, which is 1/2. So we've just got 9 over 2 on the bottom there. So we get 10 to the 9 times 3 times 10 to the minus 6 times 4 times 10 to the minus 6. And so what does that actually add up to? Well, this is 10 to the 9 minus 12 times 12, or 12 times 10 to the minus 3. So what is that actually? Well, it's 1.2 times 10 to the minus 2 newtons. Or if we were to write it out in a crude way, 0.012 newtons were being felt at this exact position. So that's it.
What do you see?
Sand?
Imagine if we could look so closely, we could see each grain, each particle. You see, there are patterns in everything.
Integrals, infinite series.
I've never seen anything like them. From an Indian...